Problem 1 of Lab 4 states, given a circular singly linked list, implement an algorithm which returns nodes at the beginning and end of the loop. You are not permitted to use an additional data structure class. So while we are about to learn about hash tables, this is part of the problem is basically saying that we are not permitted to use a hash table to solve this problem. In short, we would use void pointers and node star pointers to store the addresses in a hash table to be able to reference when we've actually found a list before. But we can't use those. So what the interviewers are actually trying to get you to understand is how to use node pointers in order to be able to perform this task without additional memory overhead. It's a little slower, but it's still in big O of n time. But the benefit is it's significantly more efficient with memory. So let's take a look at this problem. So this is a singly linked list with a circular list. And the way we have to figure it out is we have to iterate through. When we get to 22, for example, this is the node. We know where to go next, but we don't know where we came from. So somehow we have to figure out a way when we don't know where we came from to be able to solve the problem. So we can continue to iterate through, and then when we get here, we see that we have found the link. Now on the next slide, I'm going to show you something that kind of throws students off in these kind of interviews. Notice how the destination is 22 and the origin is 15 in the value. But here's the thing, we want to be looking for the addresses, not the values. So on this next slide, this is a valid singly linked list where the origin and destination are nodes with the value 22, but their locations on the data heap are different. So we want to be looking for locations of the nodes, not the values. So disassociate the data from the structure here. The first thing you should bear in mind is that the singly linked list we designed in class was designed specifically to prevent circularly linked lists from occurring. And this is a big problem in the real world. We did this by having the recursive deletion be able to pick up on memory maps. Furthermore, we encapsulated the singly linked list nodes within the singly linked list class. So therefore, you will see that I've taken the struct for the singly linked list outside, and our solution is going to involve that. Furthermore, what you will notice if you go into our singly linked list here, that in that destructor, I have commented out delete head, like so, and that's singly linked list. In the node, you will notice that I have commented out delete next, so that way we don't get a memory map trace. So I've taken out a significant number of safety precautions that our production quality rules have enforced. As a result, the objective here of this kind of problem is to see if you can help somebody with minimal experience be able to troubleshoot an issue with how they've coded pointers and nodes. So by going back to the problem, we're going to see that we have to iterate through and find a previous node. Furthermore, we have to then identify where the source and end begins. And we can't do this while storing intermediate steps, which is an additional challenge because in singly linked lists, we don't have that information. So the way we can do this is we can create two pointers. We're going to call one slow and one fast. And what's going to happen is one's going to move 2 and the other one's going to move 1. So we see that green has moved from 10 to 18, but the slow only moved from 10 to 22. And what's going to happen is we're going to keep going until these two point at the same location. If they ever point at the same location, we know we have a circularly linked list, but we have not solved the problem entirely. Another example, what about an even length? So here we're going to do the same thing. And again, we have found that there is a circularly linked list here. But now we have to consider a scenario where we have a different loop. So now we go through here again with our slow and fast. And and we actually find it, but the location that they intersect is not part of the beginning or end of the circularly linked list at all. So how do we actually do this? So what we're going to do is once they find each other, we are then going to say, all right, we're going to put the slow pointer back at the head of the singly linked list and keep fast at the same location. Now we're going to iterate one by one for both. When they meet, we will find the origin of the loop. So let's put this to the test with all of our cases. So this was our first case. So notice how the blue arrow, which originally was slow, is going to be back at the head node. When we iterate, we see that we have found the destination here. Likewise, but about an even length, we put this back slow, and they meet at 22. Again, we go here, we put slow at the head of the singly linked list, we iterate once, we iterate twice, we now have our destination. So an issue comes up that we don't have the previous node. So what you're going to see in the solution that I've presented is that we have a slow, a fast, and a previous. So what I want to show you here is the solution code that you're going to write. The first part you're going to write is this while loop. This while loop says we have our slow node, we have the head node that's being passed of the singly linked list, and we create a slow and fast node in main. And these are node pointers. We set slow and fast to the address of the head node. Here we're calling the head by reference. Then we are going to include a previous singly linked list node to track the previous value, which will allow us to be able to keep track of everything by keeping that node one node behind. Line 17 is where you're going to start here. So we're going to say while the singly linked list node fast does not equal null, we're going to say slow node is going to be slow node next, previous is going to be slow node next, and fast is going to skip 2. So what happens is we have an original, and so slow will go here, previous will go here, and fast will go here. I also have a crucial thing called a break statement. When slow equals fast, we are going to break out of the while loop. So what's going to happen is I have an if statement. If slow node is equal to slow fast, we're going to do the second part of the work here. But at line 48, I want you to note I have an else statement. This else statement says that we did not find a loop in the list. And the reason why we can claim this is because if I didn't break, meaning slow node equals slow fast, that means node fast found a null pointer, which means we don't have a circularly linked list. The other part you're going to write is lines 30 through 38. Reset slow to the head node. So just like we showed in the animation, we're resetting the head node. And then I'm going to iterate previous. I'm going to set previous is equal to node fast. Slow is going to move 1, and then fast is going to move on. So what's going to happen here is if I have a scenario like so, if I'm previous here, if I have fast here, I will set previous to point at the same node, and then slow will move 1. What will happen is then fast will move to the next one. They are now pointing at the same location. I have the destination, and previous is pointing to the previous node. So let's run the code and see what should happen. It should be make problem 1, and we see it compiles. And in main, what I'm going to show you is how it links. So in main, I've created 6 nodes. First, I create 1, 2, 3, 4, and 5, and then I have 5 pointing to the address of singly linked list node 1. So I've created the list. I've then created pointers for slow and fast. Then I run the program. Then what I do is I have 4. So initially node 4 would be here and it would be pointing to node 5. So what I've done instead is I've said that we have this 4b. I've updated it for next to point here instead. And then I had 4b point to 5. So I've added another element to test both even and odd. Then I update the list here. Node 5 points to node 3 instead of node 1. And then the last one, I set next equal to a new, which is going to make it null. So in the last case, what we'll see is that there should not be a loop. And we first see that we have updated the values. I have the address and print the data as well. And in the last case, there is no loop in the list.